This is the last one in our series of videos looking at advanced higher physics past papers. As usual, we're going to the Calder High School Advanced Higher Physics page, and we're going to click on Advanced Higher Past Papers, and the first link you see there is to Mr. Davies' interactive PDF of past papers. And once again, thanks very much to him for that wonderful resource. And as this is the last one, we're going to go to the very bottom of that table there, and we are looking at graph work and experimental methods. And in this video, we're going to have a look at 2016 question 16 and 2020 question 16. And as usual, make sure you have a go at the question first, and then come back when you're ready and you'll see how we have worked through it. So firstly then, 2016 question 16. And this is a question about a student who's doing an experiment to determine the moment of inertia of a solid sphere about an axis through its centre. So let's read it. It says a student uses two methods to determine the moment of inertia of a solid sphere about an axis through its centre. And part A says, in the first method, the student measures the mass of the sphere to be 3.8 kilograms and the radius to be 0.053 metres, and we have to calculate the moment of inertia of the sphere. And as soon as you see that word calculate, you want to be going to your relationship sheet to look up an appropriate relationship for, in this case, the moment of inertia of a sphere. And if you're looking for a relationship sheet, then don't forget we have one on our website under useful documents. There's that first link there, and you won't find the moment of inertia relationships on the first couple of pages. You've got to go to the additional relationships where you'll find the maths relationships as well, and there are the moment of inertia relationships for various objects. And we're looking for the bottom one there. It's a sphere about its centre, and the moment of inertia I is equal to 2/5 mr squared. So let's jot that down in the space for our answer. So I is 2/5 mr squared, and then we can substitute in the values that we've got for the mass. It was 3.8 kilograms, and the radius 0.053. Don't forget to square it, and that gives you an answer of 4.3 times 10 to the minus 3 kilogram metres squared. Now, if you're unsure about the units for moment of inertia, then just have a look at the relationship. In this case, it was 2/5 mr squared. So mass is in kilograms and radius is in metres, but it's radius squared, so metres times metres gives you kilogram metre squared. There's the SQA marking instructions. It's a standard 3 marker, 1 mark for the relationship, 1 for the substitution, and 1 for the final answer with the correct units. Okay, moving on, part B. In the second method, the student uses conservation of energy to determine the moment of inertia of the sphere, and the following equation describes the conservation of energy as the sphere rolls down the slope. And some of you might recognise that relationship. It's effectively just the potential energy of the sphere at the top of the slope is equal to the combination of the linear kinetic energy plus the rotational kinetic energy of the sphere at the bottom of the slope. And the equation can be rearranged to give the following expression. 2gh equals I over mr squared plus 1 times v squared. And this expression is in the form of the equation of a straight line through the origin of y equals the gradient times x, or y equals mx. Now hopefully with the projects coming back this year, you'll be familiar with rearranging an equation into a suitable form so that you can do an experiment that will give you a straight line through the origin. And then hopefully use the gradient of that graph to work out the quantity that you're looking for. So let's have a look at their experimental setup. It says the student measures the height of the slope h. The student then allows the sphere to roll down the slope and measures the final speed of the sphere v at the bottom of the slope as shown in figure 16. I've got a light gate at the bottom there to measure the speed at the bottom. And the following is an extract from the student's notebook. So they've got measurements of h, v at the bottom, and then they've got another column that's got the heading 2gh and the final column is v squared. And in part 1 says, on the square ruled paper on page 37, draw a graph that would allow the student to determine the moment of inertia of the sphere. Well, we need to think what our axes on our graph will be, and if we look back at our rearranged equation, then on our y-axis we're going to have 2gh, and on our x-axis we're going to have v squared. And then hopefully the gradient of our graph will be equal to all that stuff that's inside the brackets just now. So let's have a go at the graph. I don't like hand drawing graphs. Much easier now for those of you that have used maybe Excel to do your graphs in your project, but you may still be asked to hand draw a graph in an exam. So here we go. I'm going to put my y-axis on and my x-axis on, and I'm just going to copy and paste the last two columns in the table on so we can see everything at the one time here. So my y-axis I want to be 2gh. The units of that is metre squared per second squared. Don't worry too much about that. And on the x-axis we want v squared. And the units of that is also metre squared per second squared. Which means our gradient is actually not going to have any units, but it's the value of the gradient we need. So we're going to plot a graph of the values in the table, and of course we need a suitable size and scale for each axis. So I'm going to go up in 0.25s, which is maybe not the best idea, and I'm going to go along the way in 0.2 intervals. Now my y-axis is going to be a wee bit tricky here because each small box is going to be 0.025. So 4 small boxes will be 0.1. It's a bit clunky, but it fits it onto the screen here. So let's plot these points then. My first point was 0.18 on the x-axis and 0.39 on the y-axis. So I reckon that's about there. Remember, when you're plotting a graph by hand, you're allowed to be within a half a box tolerance. So my second point is 0.4 on the x-axis, 0.78 on the y-axis. I reckon that's about there. And let's do the third point. So 0.46 on the x-axis and 1.18 on the y-axis. Right, that's quite tricky, so that's about there. Looks a bit strange. Anyway, let's do the next one. 0.9 and 1.57. That's about there. And 1.1 and 1.96. Just about squeeze that in. So why I went up to 2 on my y-axis. And 1.1 and 1.96 is about there. Now there's an obvious point there that's kind of out of line with the other 4, and I've double checked the plotting and it's plotted correctly, so I think that's a rogue point, so I'm going to ignore it and draw a best fit line through the other 4 points. So that point that's kind of sticking out on its own there, I'm going to identify that as a rogue point, not a rouge point, a rogue point, and I'm going to ignore it. And therefore I'm going to use the best fit line through the other 4 points and work out the gradient of that line. So to work out the gradient, pick a point up near the far end of the line and a point down near the start of the line, and then we will use the points on the line to work out the gradient. Don't use any of the values in the table. There's got to be points on the line to work out the gradient. So that uppermost point that I'm using has got an x value of 1.0 and a y value of 1.75, and the point down near the start of the graph is at 0.2 on the x-axis and 0.4 on the y-axis. So if I substitute them into my gradient relationship, it will be 1.75 minus 0.4 over 1.0 minus 0.2. And if I do that on a calculator, that gives me a gradient of 1.69. Remember, that's got no units because the units on the y-axis cancel out with the units on the x-axis. So my gradient is 1.69. And part 2 there says use the gradient of your line to determine the moment of inertia of the sphere. And so that gradient we've just worked out will be equal to that bracketed term, which is I over mr squared plus 1. And remember, our gradient was 1.69. So we just now need to rearrange that relationship to get the moment of inertia of the sphere. So let's write it down again. I over mr squared plus 1 is equal to 1.69. And then if we subtract 1 from both sides, we'll get I over mr squared is equal to 0.69. And then if we do another little bit of rearranging, then I will be equal to 0.69 times mr squared. And we know what m and r are because they're written under the table there. The mass was 3.8, the radius 0.053. So if we substitute them in as well, 3.8 times 0.053, don't forget to square it, then that gives you an experimental value for the moment of inertia of the sphere to be 0.0074, or 7.4 times 10 to the minus 3 kilogram meters squared. So quite a big difference then between our calculated value and our experimental value. Let's have a wee look at the SQA marking instructions for the graph part. So 3 marks for the graph, and as usual it's 1 mark for your labels and scales, 1 mark for plotting the points, and 1 mark for the best fit line. That was just for the drawing of the graph, and there's a couple of examples of what it should look like on the right hand side of the marking instructions, with much better scales on their y-axis than I used. So, but it's shown the same pattern with the rogue point on it as well. So they're in the marking instructions really to help the markers that were marking that question. And then part 2 was working out the gradient. Now they've got gradient equals 1.73 or consistent with the candidate's best fit line. So because there's always a bit of estimation involved with the best fit line, then there will be a range of gradients that are acceptable. So as long as it matches your points and your best fit line, I got 1.69. So 1 mark for the gradient, and then the other 2 marks are for substituting the gradient into the relationship and working out the experimental value of the moment of inertia of the sphere. So 6 marks in total there for drawing the graph, working out the gradient, and using the gradient to work out the moment of inertia of the sphere. That's a bit of a monster. Anyway, moving on, 16c. The student states that more confidence should be placed in the value obtained for the moment of inertia in the second method. Use your knowledge of experimental physics to comment on the student's statement. Well, a use your knowledge question means it's an open-ended question, so there's no black and white answer for this. You just have to look at both the student's methods and then state whether or not you agree with their statement that more confidence should be placed in the second value. So here's my answer. I don't know if it will get 3 marks or not. The first method only used a single measurement of the mass and the radius of the sphere, and this allowed them to calculate a theoretical moment of inertia to 2 significant figures using the relationship on the relationship sheet. Now, there's no indication of calibration or scale reading uncertainty in either measurement, and the measuring of the radius is tricky anyway. However, the second method used a graphical method, and this shows up a couple of issues which can be confidently dealt with. The rogue point, firstly, we can ignore that, and there's a systematic uncertainty. If you have a look at the graph, it doesn't go through the origin. It's got a positive y-intercept. So, because it's got a positive y-intercept, this indicates that all the height measurements were too high, or all the speed measurements were too low. Now, there's always space at the back for you to continue your answer. So let's continue. Now, this systematic uncertainty doesn't affect your gradient. So, more confidence should be placed in the second method, as the measurements were made over a suitable range and at appropriate intervals. And the first method assumes a uniform density and radius. It might be hollow, but the second method makes no such assumptions. A graphical procedure will give you more confidence as it shows up a number of individual and systematic issues. And because you've all been back doing your projects again this year, then the graph could also have been done using a computer, where the best fit line and the gradient could have been determined by the graph plotting software, and the uncertainty in the gradient could also be determined. We could also have used the lineest function. The lineest or lineSt function would also give the uncertainty in the y-intercept, and using a computer software package would also reduce the likelihood of incorrect plotting of points and the estimation of the best fit line. Ordinarily, error bars would be required to allow the best fit line to be hand drawn, but this isn't required if we use a computer software program. Now, would that be enough to get me 3 marks? I don't know, because there's the marking instructions. No understanding of physics, no marks. A limited answer gets you 1 mark, a reasonable answer 2 marks, and a good answer, well, you would get 3 marks. So write as much as you can, I suppose, is the advice there, and make sure you try and answer the question. Anyway, let's have a look at another question. This is the 2020 question 16. Now, on the actual paper it says the 2021 assessment resource, because that was the year it was given to schools to use for the alternative certification model, but Mr Davies got it down as the 2020 paper, because that's the year it was written for. So we're going to have a look at question 16. This one's hopefully a bit more straightforward. So a student carries out an experiment using a simple pendulum to determine the gravitational field strength G, and a simplified diagram of the apparatus is shown in figure 16a. The student measures the length of the pendulum string L using a meter stick. The bob is released from point A and swings freely. The student measures the period T by timing how long it takes for the bob to swing from point A to point B and back again. And the student measures the period for a range of lengths. And the relationship between period and length is T squared equals 4 pi squared over G times L. And the student uses graphing software to produce the graph shown in figure 16b. So this time we're given the graph. Not only that, we're given the equation of the line as well. And we've got T squared on the y-axis and L on the x-axis. And if we go back and look at that relationship, then it's in the form of y equals mx, T squared on the y-axis, L on the x-axis. So 4 pi squared over G will be equal to the gradient. And remember, we can see what that gradient is on the graph because we've got the equation of the line, y equals mx plus c. So the gradient is 3.53. So all we have to do then here is using data from the graph determine the gravitational field strength. So 4 pi squared over G is equal to the gradient, which is 3.53. And if we rearrange that for G, then G is 4 pi squared over 3.53. And that gives us an answer of 11.2 metres per second squared, or newtons per kilogram. And in part 2, data from the graphing software is shown below. And we've got the gradient, the uncertainty in the gradient, the y-intercept, and the uncertainty in the y-intercept. And most of you will probably realise that that is what's called the lineest data. So if you do a graph on Excel, then you can ask Excel to give you all that data by using the lineest function. In fact, you quite possibly did that when you were doing your project this year. Anyway, we've to determine the absolute uncertainty in the value of the gravitational field strength obtained from the graph. So we need the uncertainty in the gradient and the gradient itself. And if we take the uncertainty in the gradient and divide it by the gradient, multiply it by 100, then we will get the percentage uncertainty in the value of G. And then it's just a case of taking that percentage uncertainty and working it out as the absolute uncertainty in our calculated value of G, which was 11.2. and so that gives us an absolute uncertainty of 2.2 metres per second squared, or newtons per kilogram. Let's have a look at the marking instructions for those first two bits there. So A part 1, there's our 11.2 newtons per kilogram for the gravitational field strength, and then part 2, we've got the uncertainty in the gravitational field strength of 2 newtons per kilogram. And on the right hand side it says accept the use of percentage uncertainties. Okay, moving on, 16A part 3. A second student suggests that the uncertainties in the measurement of length and period should have been combined with the uncertainty in the gradient of the line on the graph. Explain why this is not an appropriate method to determine the absolute uncertainty in the value of the gravitational field strength. Well, again, maybe from your project this year, you should realise that the uncertainty in the gradient already takes into consideration the uncertainty in both the length and the period due to the spread of the points through which we drew our best fit line. Then part B suggests 2 possible changes to the experimental procedure that could improve the accuracy of the value obtained for gravitational field strength. Well, their value is a bit high, it was 11.2, and we're really looking for 9.8. So what we could have done was repeated our time measurements multiple times at each length to find the mean period for each length. We could also have increased the length of the string, as we only measured it over about a metre, so increase the range of lengths that we used. And if you look at the marking instructions, there's a whole load of other stuff you could have said as well. For example, measure the length to the centre of the mass of the bob, reduce the angle of the swing to make it a better model of simple harmonic motion, or use automatic timing to get rid of human reaction time. So a whole range of answers you could have put there. And in part C, theory predicts that the line of best fit should pass through the origin, but the line of best fit in figure 16b does not pass through the origin. In fact, if we scroll back here and have a look at the graph, then we've actually got a positive y-intercept there of about 0.6 for t squared. So all our t squared values are too high, or all our length values are too low. Let's go back to the question. It says, suggest a possible source for this systematic uncertainty. So because there is a positive y-intercept, it means our period values are all too high, or our length values are all too low. In fact, the length values are too low because the length should have been measured to the centre of the bob. It's not just the length of the string. Again, if we look at the marking instructions, that's really all they're accepting. The period measurement is consistently too large, or the length measurement is consistently too small. That's it then. 2 very similar questions to work out physical quantities using graphical procedures. And typically there's always a question in the exam along those lines. And that is the last one of the videos in this series on advanced higher past papers. Make sure you do as many as possible before the exam. And don't forget, we've also got a whole range of other resources on our website that cover the whole course. So, but if it's past papers that you're looking for, then don't forget Mr. Davies' interactive PDF is a good way if you are revising key areas on their own. And we've got all the full past papers with the marking instructions on our website as well. So all that's left for me to say is good luck with the exam, enjoy yourself, and we wish you the very best in everything that you do.